I'm a fluid dynamicist. So the hope is that maybe I'll use a bit less jargon than someone else would. And as someone who's not an astrophysicist, I would say that kind of one of the main questions that I've been trying to figure out since I started here at this program is what is a star? Okay, so this is a big question. What I figured out so far, it seems like stars are these dots that you see on the sky. They're mostly not spatially resolved, which means that you have to be a bit clever in how you study them. So one way that you can study the light coming from these dots is to look at the light as a function of frequency, or excuse me, as a function of the wavelength of the light. So if you plot the luminosity of the star as a function of wavelength, you end up with some pattern that kind of looks like this. So there's some overall shape, but what's maybe more interesting is the fact that there are these absorption lines, and there's a lot of information in these absorption lines. So this is kind of how people are analyzing these. If you kind of zoomed in onto one of them, you would get kind of a line profile. So again, if you plot luminosity as a function of the wavelength, you end up with something. Maybe it looks a little bit like this. Okay, so you get this line. And there's a lot of information in these. One thing you could look at is kind of the typical width of the line. That has to do that line broadening. I mean, it could be many things, but one of the main things is that the broadening can be related to the sound speed, because if you have some thermal motions, that's going to broaden your lines. You can look at different lines. And the ratio of the strengths of different lines can tell you something about the temperature. For instance, if the lines come from different electron transitions and those have different temperature dependence, the ratio of the different lines tells you about the temperature. So the ratio gives you something about the temperature. The lines are also associated with different chemicals. So some stars have certain amounts of chemicals at the surface, other stars have different chemicals, and the chemical abundances can be related to the different lines that you get. Another thing is that stars sometimes rotate, and that can also lead to broadening of the lines. So this, for instance, is something that you might get from just a thermal broadening, which gives you the sound speed, but for another line, you might get something that looks a bit more like this. So here, you just kind of get your typical Doppler shift. If you have a star that's rotating in this direction, so it's kind of going like that. On this side, it's moving towards you. That's going to give you a blue shift. On this side, it's moving away from you. Gives you a red shift, so you get a pattern like this. But that's kind of degenerate between how fast it's rotating and also the direction. Because if the rotation axis is pointing towards you, so it's kind of spinning around like this, that's not going to give you any velocity towards or away from you. So you also get the rotation. You can get a rotation rate, and in particular, it's the people call it a v sine I. I here is the inclination angle, so it tells you about rotation rate and also the inclination angle. Okay, so there's a lot of information here. What people normally do is that they do atmosphere modeling, where they assume that the stellar atmosphere has various properties, and then they make a prediction of what this would look like, and then you do an inverse problem to try to figure out what these parameters are. And I understand that some people in the other program are interested in machine learning, and this is a problem that has been addressed using machine learning, and at least in certain cases seems to be very, very useful to apply those techniques. Okay, so that's the spectral characteristics of the light that comes from these dots. They tell me that they're stars. Another thing you can do is look at the brightness of your source as a function of time, and what you find is that there's kind of oscillations on different temporal scales. There's lots of different types of oscillations that you can get. If you look at the typical amplitude, I mean, in some cases it can be really small, say 10 to the minus 6, and in some cases it can actually be order unity. So some stars, the brightness changes by a very large amount. These were found a long time ago. People noticed, kind of ancient astronomers noticed that there's certain stars where the brightness changes very obviously on the time scale of days. But what we've been looking at more recently is kind of these stars that are the brightness is changing a bit less. And for those, something that can be very useful is you take a Fourier transform of the signal. So in that case, you get the Fourier transform of the luminosity as a function of the frequency omega. And here you find that you get these lines. Okay, so these are all oscillation modes of the star. So just global oscillation modes of the star. And what people look at is what's the frequency of these. So far, I would say no one really looks at the amplitude. That has kind of been a bit too hard to interpret. But in terms of the frequency, people think about the frequency as being parameterized by three things. One is you think of these oscillation modes as their angular structure is given by a spherical harmonic. So it's a YLM. So L here is the spherical harmonic degree, and M is the azimuthal wave number. And then N here is the number of radial nodes. Okay, so there kind of becomes a game that you can play of you see all of these oscillation frequencies, and you try to figure out what's the structure of a star that would give you these oscillation frequencies. And it can be very useful to try to identify for each of these what's the N, L, and M associated with them. Now, a big disadvantage of these dots of light is that they're not spatially resolved. That means that we can't actually figure out directly what is the angular characteristic of these modes. You're actually taking an average over them, and when L is high, that average actually wipes out a lot of your signal. So really, the only thing that we're seeing here is kind of like L less than or equal to 3. Okay, so it's not as much information as there could be there, but that's basically what we have. There's basically two types of modes that people are looking at. One are the sound waves. Those are called P modes. P because the restoring force is pressure. And the other one are the atonal gravity waves, which are called G modes. Okay, you might ask yourself, well, what about rotation? An important thing is that in stars, the buoyancy frequency is often much larger than the rotation frequency. So people normally think of rotation as just giving a perturbation on these different signals. Okay, so let's talk about some properties of stars. And just as an example, I'm going to give some properties of the sun. Mass of the sun is 2 times 10 to the 30 kilograms. Radius of the sun is 7 times 10 to the 8 meters. The luminosity, I guess that's probably also important for climate science. 4 times 10 to the 6 watts. And something else that's pretty important is the energy that's released by nuclear reactions. So in the sun is powered by fusion between hydrogen into helium, and that releases energy at a rate of 10 to the 14 joules per kilogram of hydrogen. Okay, so from these numbers we can come up with some important timescales that can give us some insight into what's going on in the sun and also in other stars. So the first thing that you could consider is kind of what's like a gravitational timescale. So if you're at the surface of the sun, the gravitational acceleration is given by the gravitational constant m over r squared. And if you have that acceleration from the surface all the way to the center, then the amount of time it would take for you to fall to the center, which is 1/2 a delta t squared, is equal to r. So that means that you end up with a time scale, delta t, which scales like square root of r cubed over gm, and this is referred to as the dynamical time. And for the sun, this is about 30 minutes. Okay, so that's the first important time scale. Time scale 2. The second time scale we want to estimate is a thermal time scale. So for that, we can calculate the thermal energy. Well, the energy from the sun, the thermal energy, it comes from the fact that you have gravity, which is pulling you inward. So we're going to say that the thermal energy is similar to the gravitational energy. And that's given by gm over r. And we know how much energy is leaving the sun. That's the luminosity. So you can come up with a thermal timescale, which is equal to the energy that's available, the amount of thermal energy that's available over the luminosity. So that's how much time would it take to lose all your thermal energy. And that is about 3 times 10 to the 7 years. Okay, so much longer than the dynamical timescale. Last timescale is the nuclear timescale. So the amount of energy that's available for nuclear reactions is given by Q times the mass. Now, not the entire mass is hydrogen, and not all of the hydrogen ends up getting burnt, but just for order of magnitude, this is going to be Q times m. That's the amount of energy associated for nuclear reactions over the luminosity. So this is kind of like the lifetime of the sun. You get 10 to the 10 years. Okay, so we're in this limit where the dynamical time is much shorter than the thermal time, which itself is much shorter than the nuclear timescale. Okay, so my understanding is that when people are thinking about climate on Earth, what you're interested in is kind of things that are longer than dynamical timescale, but shorter than the thermal timescale. For stars, people are actually interested in things that are longer than the thermal timescale, but are comparable now to this nuclear timescale. So this is the timescale of stellar evolution. So what I mean is that we don't care about kind of the sound waves or convection. Those are kind of like really fast things. We're interested on some like longer time scale of what's going on. Okay, so here this is what I'm going to call the time scale for climate on stars. Okay. Okay, so now next thing that I want to discuss is stellar structure. Okay. So on this long time scale, how can we describe stellar structure? And the way that people do this is similar to you might call this like a single column model. So we're going to take the spherically symmetric structure and just look at how things depend on radius, just one-dimensional. A better model would be to think of a star kind of like as an aquaplanet, where kind of all the forcing is only happening on large length scales. The departures from the spherical symmetry, it's basically due to rotation, maybe also a large-scale magnetic field. So the differences of like forcing on the system is only on large scales, but I'd say that those are kind of perturbation effects, and that this sort of single column model is actually remarkably good. So what can you do? Well, remember we said that this dynamical time scale is short, and that means that you are going to be in hydrostatic balance. Okay, so dp dr is given by minus g m rho over r, where here this m, that's what's called the enclosed mass. That's the mass within radius r. That can be related in a straightforward way to the density. As shown here. Okay. So we have r squared. Gm over r squared. Thanks, Lars. So this is an equation for pressure, and we know what m is here. So if we knew how the density changed with radius, that would solve the problem. So we need something that's like d rho dr. It turns out that actually what's easier to get instead is an equation for the temperature. And then once you know the equation for the temperature, then you use an equation of state. So that's rho as a function of T and P. Okay. So the equation for the temperature, that's kind of where all the action happens. I'm going to tell you that it depends on, well, the way you get this is that this comes from the energy transport. Okay? So first we need to say how much energy is there that you need to transport. And the energy comes from nuclear reactions. So the luminosity that goes through a certain radius is given by 4 pi r squared rho times the nuclear reaction rate. So this is the energy generated by nuclear reactions per mass. So multiplied by the density to get per volume. And so this tells you how much luminosity has to go through at each point, and then we're going to try to figure out what the temperature gradient is by seeing how that luminosity actually gets transported. So because we're assuming that we're looking at timescales that are longer than the thermal time, so now we're going to use the fact that the thermal time is short, then that means that we are going to be in thermal equilibrium. That means that the total luminosity has to be transported by something. It turns out that there's only two choices. One is it could be transported via radiation, and the other is that it could be transported by convection. Okay, so if it's transported by radiation, what does that look like? Well, that's actually pretty simple. The luminosity transported by radiation, that's given by 4 pi r squared times the radius of diffusivity, K, times the temperature gradient. Okay, so then you can rearrange this and solve for what the temperature gradient would be here. So what people define is this minus dt dr subscript rad. So this is like a radiative lapse rate. So I'll write it as a gamma rad. Although in astrophysics people normally denote this as grad rad. But it's just a lapse rate. So you can calculate what's the lapse rate, what's the temperature gradient that you would need if the entire luminosity was transported by radiation? So that's this right here. Okay, so this is the radiative lapse rate, and then if you had convection, then you could calculate. Well, we know that the luminosity carried by convection, that has to be equal to the total luminosity minus the radiative luminosity. Okay, and then you need to have a way of getting from the convective luminosity to a convective lapse rate, and the way that this is done is using what's called a mixing length theory, and I don't have time to get into that here, but I'll just say that in the simplest model, you say that the convection mixes things towards being adiabatic, so that this is just given by the adiabatic lapse rate. Okay, so this is kind of the idea of the energy transport in stars. It's either by radiation or a combination of radiation and convection. So that means that this temperature gradient is given by either minus gamma rad. So it's either the radiative lapse rate or it's this convective lapse rate. Okay, how do you pick which one is actually realized? Well, what you do is that you imagine that the luminosity is transported by radiation, and then you calculate what's the potential temperature gradient. And if that's negative, that means that you're unstable to convection. So then you have to switch over to the convective lapse rate. Okay. So now these are 4 equations plus your equation of state. If you combine these with boundary conditions, that's enough to solve for the structure of a star. Now, what we're interested in is stellar evolution. And you might know that there's no time dependence here, at least not yet. Where does the time dependence come in? Well, that actually comes in once you look at the evolution of various chemical species. So, for instance, you could write down an equation for the evolution of hydrogen. So it's just an advective, diffusive reaction equation. Okay, and this is kind of like where the main time dependence comes in, because these nuclear reactions, they're going to be converting hydrogen into helium. So you can write another equation for concentration of helium, and you could also do one for like carbon, oxygen, everything else. And basically these reaction terms are going to change the compositions of the gas, and then that's going to then change what the reaction rates are. Okay, so that's kind of how everything becomes time dependent. And I guess one last thing is that typically people don't actually look at the advection of these species. Instead, they parameterize this in terms of a turbulent diffusivity. So this turns into minus grad turbulent diffusivity times grad H. Okay, so this is basically all of stellar evolution for you. And I guess now the question is, now that you have everything here, it's kind of like, well, what do we not know? And there's 2 types of things that we don't know. One is the microphysics. So that's something like, what is this equation of state? And by the way, the equation of state also depends on how much hydrogen, helium, etc. that you have. It's not just temperature and pressure. This radiative lapse rate, that has to do with this rate of diffusivity. Okay. And what else? The nuclear reaction rates. All these things, this diffusivity, I mean, these things, they basically come from lab experiments, and but for very, very strange states of matter at very high temperatures and pressures. So these quantities are actually not super well known. Okay, so that's that's one major question for what's going on in stellar evolution. The other thing, which is what I'm going to focus on in the second half here, is what I'll call like a sub-grid scale modeling. Okay, so that's something like what is this convective lapse rate, and what is the turbulent diffusivity for this for the different chemical species. Okay, so these are things that that should really come from multidimensional simulations, or at least from some multidimensional theory, and that needs to be parameterized and then put into these stellar structure models. Okay.
Any questions? No.
Okay. Okay, so I've kind of talked about kind of the broad structure of stars, and now I want to talk about transport. So that's we're kind of getting towards the meat of this program that's occurring right now. And the transport question that I want to discuss is a question of chemical transport. So it's this DT term right here, and in particular, I want to discuss transport associated with convective boundaries. Okay, so just as some background, if you solve these equations for different types of stars, I guess the first one that you can look at is a star that looks like the sun, and for the sun, you end up with a structure that looks kind of like this. So the outer part of the sun is convective, and the inner part is stably stratified. So you have nuclear reactions happening in the inner part of the sun that generates the luminosity. That luminosity is initially transported via radiation, and then at a radius greater than about 0.7 solar radii, radiation can no longer transport the entire luminosity, and then it becomes a mixture of radiation and convection out to the surface. Okay, so this is what's happening for a star like the sun. Okay. What happens for a more massive star? Okay, so this is my model for a more massive star. Pretend that these are circles. A more massive star, you end up with a small convective core and a stably stratified envelope. Okay? So here the luminosity is so large that this radiative lapse rate becomes really large because the luminosity is really large, and it becomes so large that you can't carry all the flux via radiation. So in this case, you have a convective core. So this is a sketch. For instance, if you had a star that's 4 times as massive as the sun, the radius would be about 3 times the radius of the sun. And then in this case, you're going to have convection when for radii less than, say, like 15% of the star's radius. Okay. So I guess this. You might say it looks maybe kind of like the ocean. You have like a mixed layer at the top where you have all this turbulence, and then the inner part is like the abyssal ocean where you're stably stratified. Here, maybe it looks a bit more like the atmosphere. You have your troposphere in the middle. You have convection, which is below the stably stratified region. You might think of it like the stratosphere. And basically, we're trying to understand what's going on at the tropopause. So, as I said, we're specifically interested in chemical mixing. So the picture here is that as a function of radius, if we put our core radius here, as this star evolves, it's burning hydrogen into helium in its core. That means that if you have some small level of helium out here, outside of the core, you're going to have a larger amount of helium inner part, inside the core. But the total amount of material has to sum up to 1, so the concentrations of hydrogen and helium have to sum to 1. So that means that the hydrogen concentration kind of looks like this. Okay, so this is CH. Okay, so that's so this is kind of like the 0th order picture of what's going on. But now imagine that you had some extra mixing process near this interface. Well, that means that you might be able to mix some of the helium into the stably stratified region, and that means that in the core, there's going to be actually less helium, right? Because there's only a certain amount of helium that you generated so far. So then, if you look at the hydrogen, that actually means that in the core there's going to be a larger amount of hydrogen. Okay, and this, it turns out, this extra hydrogen here is really important. So if you have more hydrogen, that means that you get more nuclear reactions. Okay, this is going to change the lifetime of the star, and it's basically going to alter the subsequent evolution of the star. Why do people care? Well, these massive stars are really interesting for astrophysicists because at the end of their lives, they can explode as a supernova. Okay? Supernova are seen all across the universe, so understanding the properties of the stars that turn into the supernova is really important for astrophysics. Another thing that's been very popular recently is that when you have two black holes, which can also be produced by these massive stars, if they're close to each other in a binary, they can merge and produce gravitational waves, which have been recently observed with LIGO. So the astrophysicists, they're really interested in these massive stars. You want to understand what kinds of black holes are these making, what type of supernova are they going to make, and this is intrinsically linked to this chemical diffusivity that you get near the boundary of your convection zone. Okay, so the big question. So our question is, what is dT near the boundary? Okay. Oops. Yeah, I think it maybe just didn't pull hard enough. Okay. Thanks, Lars. Okay, so now I want to discuss two different ways that people have been thinking about what's going on at the boundaries. The first way is using observations, and then the second way is using numerical simulations. So the observations that I'm going to discuss are this fancy astroseismology, where we're looking at the different oscillation modes of the star. So for these massive stars, what's nice is that the exterior of the star is stably stratified, and that means that we can get G modes, gravity waves. So we're going to talk a little bit about some G mode astroseismology. Okay, so how do you model these G modes? Well, what is important is the structure of the buoyancy frequency as a function of radius, and simplest 0th order model is that it's equal to 0 up until the core. This is the radius of the star out here, and then let's just assume that's constant and equal to n naught in the radiative envelope. Okay. Well, the modes that are observed have frequencies that are much less than the typical buoyancy frequency. So because of that, we can use the following expression for the dispersion relationship of the waves, that the frequency is given by the horizontal wave number times the buoyancy frequency over the radial wave number. And then we can solve this for the radial wave number, kh and naught over omega. And for the radial part of the wave, remember that these are given by spherical harmonics. So when you take angular derivatives, that's related to the spherical harmonic degree. So this is going to be L times L plus 1 over R times N naught over omega. And for notational simplicity, this combination of L times L plus, the square root of L times L plus 1, I'm going to call that capital lambda from now on, because it's going to show up. Okay, so this is the radial wave number. Now we can do WKB theory to try to solve for what's the radial eigenmode that you might get for a G mode in this sort of configuration. So for that, the radial velocity as a function of radius, I'm going to write that as sine of integral. So we're just going to be integrating kr with respect to radius. We're going to integrate from the surface down to a radius r. And then the wave number is lambda n naught over omega. And then we got dr over r. Okay, so what's the condition to have an eigenmode? Well, we're going to assume that the boundary conditions is that the radial velocity is 0 on both sides. So this is automatically 0 when r is equal to r naught, because you're integrating from 0 or from one point to itself. But then the condition to get the eigenfrequencies is that that the radial velocity at RC is equal to 0. And that means that this integral from the surface of the star to the convection zone of lambda n naught over omega dr over r has to be equal to n times pi, where n here is an integer larger than 1. Okay. What's convenient is to define the period 1 over omega, and then the period associated with mode n satisfies the following equation, that Pn integral from r star to r convection gamma n naught over it's just gamma n naught times dr over r is equal to n times pi. And what's nice about this is that you can just divide this, and you can see that when n changes, it's only this value here that changes. So you can write the difference between the period of two adjacent modes, so that's Pn plus 1 minus Pn. That's delta P. That's, I'll just say that it's proportional to 1 over lambda times the average of the buoyancy frequency. Okay? And indeed, if you plotted the Fourier transform of the luminosity versus frequency, versus this period, what you would find is that you end up with modes that are about equally spaced in period. Okay. What's a little bit more interesting is to plot delta P versus the period. Okay. So just taking the difference between these as a function of period. And according to this simple theory, what you would get is something that's just constant like this. Okay. But it turns out that that's not what's seen. What's actually seen is something that looks like this. Okay, so most of the time you get something that's equal to this delta P, but you can see that every once in a while you have this dip. Okay? And so what I want to talk about quickly is kind of what causes that dip. Okay, I should also say that at this stage, you haven't actually gotten too much information about what's going on near the core, because all you have is the average value of the buoyancy frequency. That doesn't tell you like where the core is or anything like that. So it's actually good news that you have these dips, because those let you get a lot more information about what's going on. So why do you get this? Well, it actually has to do with the evolution of the helium concentration over time. So when you start off at the beginning of the star's life, it's pretty uniform, but then you start to get some you start to get some nuclear reactions, which raises the helium concentration in the core. Now, what's interesting is that not only does this happen, but as the star evolves, the core actually shrinks a little bit. So the next amount of time when the helium concentration rises, it doesn't actually rise to the same radius. It actually only rises in a smaller region. It kind of goes like this as the star over the star's life. So kind of a better model would be that the helium concentration kind of looks like this. Okay, so it's about constant in the convection zone, about constant in the radiative zone, but then there's some region in between where you have this change in the composition, where you're going from more helium down here to less helium down here. Okay, and that is that gives you extra stable stratification, because the helium is heavier than the hydrogen. So if you turn this into a buoyancy frequency, what you end up with is that the buoyancy frequency is 0 in the core. Then you have a big spike, which I'm going to write as NC. So that's the buoyancy frequency due to this composition. And then you get to our old friend N naught out here. Okay, so this is the radius of the star, and then you have some interface here, and this region here has a width of delta R. Okay, so that's this region here has width delta R. Okay, so how does this change our calculation that we did over here? Well, as before, our eigenvalues, to get the eigenvalues, we want the condition that the radial velocity at the convective core and the radial velocity at the surface are both equal to 0. Now we have this jump in the buoyancy frequency right here, so we need to apply a matching condition. The matching condition is that the radial velocity and the pressure are continuous. Okay? If you do that, you end up with the following expression in order to satisfy this. So that the tangent of the integral, so it's the same sort of integral as before, except now we're integrating from the surface to that interface position of n naught lambda over omega dr over r is equal to minus n naught over, I'm going to write the NC's in blue, just to try to make it a little bit more clear. Tangent of, now we're only integrating from that interface radius to the core of NC lambda over omega dr over r. Okay, so this is the condition now, and the key thing is that the n naught over nc is much less than 1. Okay, nc is really large. Okay, and because of that, to leading order, what you get is that the tangent of this expression here is equal to 0. Well, that's the exact same thing that we had here, right? When tangent is 0, so is sine. But there's a perturbation, and the perturbation that you get that the change in the period difference, it's going to be proportional to delta r over r R star minus Ri. So that's the difference between, or the ratio between this radius difference and this radius difference. And then basically you're going to take a derivative of this tangent. And there's a minus out here, so you get minus, and then you end up with secant squared of this expression, so integral Ri to Rc of NC lambda over omega dr over r. Okay, so what does this mean? Well, what it means, so you have this minus secant squared. Secant squared, that's of course positive. That's exactly what these dips are. Okay, so that's the minus secant squared. And then, so the period spacing between those dips, that's related to what the value is for this convective buoyancy, or the compositional buoyancy frequency. And then the magnitude is related to kind of the size of that region. Okay, so the presence of these dips gives you a lot of information about what's going on right next to this interface, and you can then use that to infer properties of that diffusivity, turbulent diffusivity. Okay, and so this is just an outline of how this works, but there was much more careful work done by my Pedersen, who's right here, earlier this year. She analyzed 26 different stars and found that turbulent diffusivity plays an important role in the region next to the convective boundary, maybe 10 to 20% out from that spot. Okay. So what else do I want to talk about? So that's kind of like the theoretical, or excuse me, that's the observational way to probe this. Oh, I messed this up. So that's how you get that from the observations. The way that you try to probe this from the theory, what you can do is try to just run some simulations. So the simulations are of just this core region. Okay, so you can do a simulation of that convective core. What people found is that you end up with this kind of dipole flow. So you get convection outside, you're stably stratified, so you got some waves. Okay. And I guess I want to mention that there's a lot of numerical challenges associated with this. The first is that you're in spherical geometry, so that's tough. The second is that you are at low Mach number. Many people use codes where they explicitly solve for the sound waves, so that makes it really tough. We're looking at Mach numbers of, say, like 10 to minus 3, 10 to minus 4. For the stellar evolution, we're interested in things that are on timescales long in comparison to the thermal time. But the thermal time is much longer than the dynamical time. So a major challenge is that the thermal time is very long. So we're really trying to make a prediction of what's happening on the thermal time, but that's hard to access via simulations. And then the last thing is that the flow is very turbulent, and this is maybe a place where some machine learning closure models might be able to help you out. So what do you actually do to try to get a turbulent diffusivity from a simulation like this? Well, what you could do is you could initialize some dye outside of your convection zone, solve an advection equation, and then you just kind of like let it evolve forward in time, and what it will look like after a bit more time. So it's going to kind of spread out a little bit, and if you then plot kind of spherical average as a function of radius, you start off with just a spike outside of the convection zone. And then if you let it evolve in time, it's going to smear out a bit. Then in the convection zone, the mixing is very efficient, so it's going to be almost homogeneous there. Okay, so the question is that this U dot grad C, can you model that as a turbulent diffusivity? So you can model this as like a minus divergence of dt times grad C, or like the average of C. And it actually turns out that this turbulent diffusivity approximation is pretty good. So if you and then if you plot what that turbulent diffusivity is as a function of radius, if you have the convection zone here, it takes some large value in the convection zone, and then it starts to fall off very quickly. So I'll actually plot log of that diffusivity. Okay, and then so it's maybe falling off exponentially, maybe faster than exponential, something like that. Okay, so this is something that you can do, and then you can try to take this and put it into our stellar evolution model right here, and then ask, does that match up with what's going on in the star? I would say that so far the answer to that is that's not very clear. So so this is kind of an example of where people are going and what we're trying to figure out. One last thing that I wanted to mention is that it would really help if we had a physical mechanism of what was going on that gives you this turbulent diffusivity. So one idea that people have was Kelvin-Helmholtz instabilities occurring at this interface, but the Richardson number is like 10 to the 4, so that seems a little bit tough. Another possibility would be something like Humbo instability. So something that people have thought about as well is separation flow, because you end up with a flow which kind of hugs along this boundary, and then it has to detach. And it seems like there's some interesting entrainment or mixing going on in that region right there where it detaches. Okay, so I'm kind of running out of time. So I think I'll pause here. I just want to say, just in a few words, some of the other transport questions that people are interested in. One is momentum transport. So by looking at the rotational splitting of these lines, these astroseismic lines, you can see them a bit over there. You can measure the rotation rate in the outer part of the star, the inner part of the star. Those are not the same. So there's some angular momentum transport occurring there. And then one last thing would be energy transport. So this mixing link theory, how do you get from this convective luminosity to a convective lapse rate? That's a major problem that people are working on, both observationally and also theoretically. So I'll pause there and take any questions.
Questions, please. Hank, hang on.
Yeah, thank you very much. It's okay. Okay. So there was a nice talk. There's actually quite some overlap, between the two programs. So that's very nice. Now I was wondering, in the numerical simulations, to what detail can you resolve, the relevant scales for actually sort of capturing the turbulent transport?
Yeah, that's a great question. So to what extent can you resolve these scales? I said the turbulence was a major challenge here. I guess the good news is that the system only has one length scale associated with it, which is, it has two length scales. One is the size of the convection zone, so RC, and then there's another length scale which is the boundary region. And this is actually really small. Okay, so I would say that this is a big challenge. And in particular, what you would want is you'd want the to accurately resolve the turbulence that's occurring on that length scale. I would say that has been hard. People have, I think there's good evidence that people are doing this. Early in the program, we had some discussion from the group of Falk Herwick and Paul Woodward, where they presented some simulations with resolutions order 1,000 to maybe 1 to 2,000 across this convection zone. So from that you can get you can get some nice turbulence. But something that has been reassuring, I think, is that whenever people do resolution studies for this problem, I think that this turbulent diffusivity seems to not change very much with the resolution. So I think we might kind of like be in the sufficiently turbulent regime for that.
So in the picture that you just erased before, you had mentioned there was some, it was important that you'd have excess hydrogen, I guess, because there were more reactions, but I didn't quite understand what the baseline was. So it's excess hydrogen with respect to what? I mean, I saw you had some heaviside functions, but what was that baseline? Yeah, so that's a great question. So I guess maybe drew it a little bit up here too. When the star is born, it's formed from a cloud of gas, and that gas it's a mixture of hydrogen and helium. It's mostly hydrogen, but it does have a bit of helium. So even when the star is born, it has kind of helium a bit everywhere, but then it really gets enriched in the core. Does that answer your question? Maybe not quite out, but that's fine. Okay, sorry. Oh, I see. Okay, yeah. Okay, yeah. We can talk later.
Just like, so if the resolution doesn't matter all that much and you're getting the curve, why you want to know what is the turbulent mechanism?
That's a good question. Some people say that they don't care, and it's just kind of like an empirical fit. I guess for me, I'd say that an advantage of having a mechanism is that you could try to apply it to simulations that we haven't yet run. So two things that I haven't mentioned very much is rotation and also magnetic fields. So every star is rotating, and oftentimes the rotation frequency is comparable to this large-scale convective frequency associated with the large-scale convection. And especially for these massive stars, the rotation frequency can often be larger. Okay, so rotation is a very strong effect. Some people are running simulations with rotation. Some people haven't yet. So if we could understand where this comes from in the non-rotating case, and we have a physical mechanism, I think it might help you have a better idea of what to expect in the rotating case. And then also, these stars are magnetized plasmas. Very high conductivity, and because of that, the magnetic fields can also change everything that's happening as well.
On the left, it's still like marked in red, microphysics. Is the microphysics not understood, or is it just hard to connect it to the large-scale phenomena?
I would say that's not understood. People are recalculating these equation of states. The radial diffusivity is not known. Every few years, there's new radial diffusivities which are released, and when that happens, it breaks everyone's stellar models. So these are things that are still being calculated theoretically. They're still being measured in labs. So this is something it's a real uncertainty, and hopefully that's getting better with time. So I just wanted to point out that's one of the big sources of uncertainty that kind of we're not really addressing so much in this program, which is mostly on this kind of subgrid scale modeling.
Sorry, Jim. Just hang on.
Are you learning anything that might be relevant to fusion reactors on the surface of the Earth? Are there similarities in these complex dynamical problems the interactions between turbulence and radiation, is that a line that's being pursued, or is it worth pursuing?
Yeah, that's a really great question. I would say that one of the big differences between what's going on in stars and what's going on in fusion reactors on Earth is that fusion reactors on Earth, the plasma is very tenuous. The densities are very low. And because of that, things are not very collisional. Whereas in stars, things are much more collisional. The fluid approximation is a good approximation. So because of that, I would say to leading order, the problems are kind of different. However, there are, of course, MHD instabilities which are occurring in plasma devices that also occur in stars, and there's some connection there.
I was going to say stars have figured it out and we haven't. But okay, thank you, Daniel.